Okay, so you already see the title about collapsing towers for site channel security.
Sorry, let me pull up my notes.
Cameron will present the paper.
Yep.
So,
Yeah, so thanks. So this is a small part of a much larger project with everyone on the slide you can see right now. So the bumper sticker for the next 10 minutes, however long, is we want to use staging to detect side channels. And when I say side channels, I specifically mean timing side channels. There's all sorts of side channels, but we're only worried about timing. And specifically, even more specifically, we care about microarchitectural side channels. So for those of us who haven't spent the past however long thinking about how horrible computers are, here's an example of what's called a Spectre vulnerability. So just to kind of elucidate the problem statement a little bit more, we're going to have some kind of secret value in memory. This could be some kind of password and encryption key. For the sake of this example, it's just a secret number. And we have a user who gets to interact with the program at this very clearly defined point. And we want to make sure that the user can't learn anything about the secret. So just looking at this, this is really easy, right? Like, the word secret doesn't appear anywhere in this program. How could it possibly leak anything? Now, since I opened by talking about side channels and microarchitectural side channels, the first thing you might notice is, okay, this secret value, depending on how the compiler might lay it out, this secret value could come right after this public array in memory. Which means that if we can get the program to read from pub sub 8, then we could be in trouble, right? We've influenced the behavior of the program by reading from this secret value. But that's not to worry. We have this if condition right here that guards against this out-of-bounds read. But thanks to the magic of branch prediction, where hardware might decide that actually I don't have to check this branch prediction just yet, we could initiate this memory load before we realize that we shouldn't. So we're going to go under the shadow of this if condition, start reading the memory load, and then we decide, oops, actually we shouldn't have done that. And this is going to affect the hardware cache, right? We're going to load this pub sub secret into memory, which means that if the user guesses what the secret is and they decide to input that, then that's a cache hit. And if they can clear the cache and run this over and over again with a bunch of different guesses, then one of those runs is mysteriously going to be faster because one of them is going to have a cache hit and the rest of them are all going to be cache misses, which means they've now learned the secret. So how do we catch this? The really scary thing about this vulnerability is that this relies on a particular combination of hardware components, right? If we just look at the surface language, we actually did guard against the out-of-bound read. So this is not only an out-of-bounds read, this is a phantom out-of-bound reads. Particularly, this manifests from the fact that a phantom load will affect the cache, and this effect does not get unwound when we find out that we shouldn't have gone under this branch. So the classic way that we solve this is we're going to design some kind of cost model that we know about caches now. We know about speculation now. We have some really fancy analysis. And there's a lot of work on that. I'm not going to get into it. That's not really the topic of this talk, because we're going to do something different. What we want to do is we're going to say, here's an input program. I want to do some pre-processing on this input program such that I have some intermediate representation that includes all of these hardware effects. We're going to write them into the thing that we're analyzing. So what I mean by that, well, if we go back to this example, the key thing that went wrong was that this read here side effected some global state. Particularly, it loaded something into the cache. So why don't we just insert some code that tracks the cache? So how are we going to do that? How are we actually going to do this transformation? Well, the answer is staging. So I'm going to shift gears and kind of talk about what we've actually been doing so far. The plan is we're going to start with a hardware interpreter. For the sake of today, we're going to take in some assembly program, some input, and we're going to produce the output of the program, and we're going to produce some number of ticks. I'm going to be intentionally vague about what constitutes a tick here. It could be interpreter cycles, it could be hardware cycles, whatever level of granularity you want, and you can include whatever hardware effects you want, speculation, caching, blah, blah, blah. Next, we're going to add some staging annotations. I'll explain what that means in a moment. And this is going to transform this interpreter that we started in into a compiler that takes in our service program and produces what we call a residue program. This residue program is then going to take in the true input of the program and then give us the same timer and output as before. So effectively, we've curried our interpreter and specialized it to the program we want to analyze. And the key thing here is that this residue program is just a standalone program, right? We have some intermediate representation, we spit it out, and this is now our artifact that we're doing our real analysis on. And the timer here is now just a first-class output. right? We're just going to have a program that spits out a number, which means that we can use any kind of non-timing aware, non-hardware aware classical analysis we want to enforce properties on this number. For example, that it's not influenced by any kind of secret. So as a more concrete example, here is some of the actual code from our proof of concept. We're gonna, you can see we match this instruction. If it's an add, we're gonna do an addition. Then we're gonna add these rep to the type. So if you're not familiar with stage programming, and particularly staging with types like in Scala LMS here, what this rep means is that if we have a value of type rep sub t and we manipulate a rep sub t, we're adding nodes to some internal syntax tree instead of doing a real computation. And this return type of rep sub unit here means that we're going to return that syntax tree as the result of calling this function. That syntax tree then gets spits out. That's our residue function. Congratulations, we've now staged an interpreter. This is a like quote unquote hardware compiler for some definition of compiler. So here in the bottom right is what the output of this particular case might be if we choose to exercise it. And you can see how the timer, this is just like a straightforward timer plus equal 1 that gets reflected into the resume, as well as this addition that also shows up. But this instruction dispatch, where we actually check what kind of instruction we're looking at, that's not there. We just emit a straightforward addition. So for the actual analysis then, this is the driver from our actual proof of concept. I'm not going to go over all the details of what's going on here, but this is basically, this is a regular assert that we're using with an off-the-shelf bounded model checker. Doesn't know anything about timing. We're just checking a regular struct value that happens to be named timer. And we're enforcing that, between two different runs with two different secrets, the timer is the same. Now, at the beginning, I promised that we're going to do caching speculation. Then I just show you an example that's a timer plus equals 1. So how can we extend this to deal with caching? Well, on screen is this memory load case from some of our proof of concepts, and I want to highlight this getMem function. With the magic of object-oriented programming and overloading, we could just do the naive thing. We have some memory in our state struct, and we're just going to read it. Or we could write a cache simulator. This is, again, very straightforward, and you can see there we have this timer plus equals 100 saying that a cache miss is expensive. This, too, will get reflected into the residue normally, which means that, again, it's just a straightforward value that the bounded model checker is going to see, OK, that's a plus 100, that's bad. So we didn't do anything special, right? We just wrote another interpreter. I'm going to claim an interpreter is easier than writing a new analysis. If you disagree with me, well, I don't know. I'm not going to show speculation because it doesn't fit on the slide. It's kind of messy. It's in the paper if you want to see it because we have to hook into the interpreter loop, but it's not that much more difficult. Kind of works the same way. So concretely, what have we actually managed to do? We can detect timing leaks from all sorts of different vulnerabilities that involve different combinations of caching and speculation. We have one that's just a naive timing leak. We have one that only shows up with caching. We've detected the Spectre vulnerability I showed at the very beginning. Our infrastructure is also very modular. We can use all of your favorite software extensibility tricks to swap out components. So this is kind of our value add here. We didn't have to design a new analysis. All we did was we wrote a cache simulator and plugged it in. What have we not done? What are our future directions? So the big one is that we've written, so far, all of our hardware interpreters by hand. Real hardware is like messy and complicated, and writing a staged interpreter, or even just a regular interpreter, for these is very messy, very complicated. So what we want to do is be able to generate a staged interpreter from some kind of HDL. I don't know, pick your favorite HDL, Verilog, whatever, we want to do that. I also mentioned that we can use any kind of classical analysis on the residue. So far, we've kind of only used bounded model checking. We have some kind of experiments with taint analyzers, data flow analyzers, program slicers. So that's an exciting new direction that we're working on. And the biggest one is that we want to move more of the analysis into the staged interpreter itself. So far, we just wrote an interpreter and stuck some labels on it. But there's some exciting work about using this same technique to turn an abstract interpreter into an abstract compiler. And we want to kind of apply the same methodology to kind of transform the input to a way or to a form that's more amenable to analysis. Maybe there's some knowledge that we can know at runtime that we can reflect into the residue that makes the analysis easier. So what are the takeaways? Side channels are hard, in my opinion, because they require reasoning about a lot of different interactions between different components. We get some kind of n-squared problem. So instead of writing n-squared different models for all these different interactions, why don't we just have a system that allows us to expose the details to our existing analyses, right? No new analysis, we're just gonna lift everything to the surface where our existing analyses can seize them. Staging is a great way to do this. We have a bunch of levels, and staging is a great way to collapse them together so that everything's visible. And yeah, that's collapsing towers. Thank you so much.
Okay, thank you very much for the presentation, keeping the time limits. So, are there questions? So Seth.
So, your system makes it easy to detect when there are possible timing attacks. What about, have you thought about building a system that just rules them out statically?
So the question is, have we like tried fixing the things we detect? No, this is detection, not mitigation. So one of the big flaws in this technique is blame is very hard. If I have some surface program and I say there's a leak on this hardware, we have no idea whether the leak is the hardware's fault, the surface program's fault. Where would we even begin to fix this? This is something that we like have on the horizon, but it's so far like not really a goal.
So I have a question. So you have already mentioned it in future work. So how can you describe the different kind of leak? But there has been some leaks detected in the last year, and how positive you are with your method that you can detect them, or also in the future.
I'm not sure I understand the question.
So if you look at the problems that have been detected with caching and so on, and sometimes they have been fixed. So it's on the practical side. So do you think you can, from the existing attacks, you can detect them?
So one of the like end goals of the larger project here is for iteration of these systems. So if someone detects a new vulnerability with some specter mitigation technique and it turns out not to work. Right now, the way that you use formal methods to say, okay, we actually fixed the problem, is you sit down and someone thinks really hard and you spend a year writing a new model, and your formal method said, cool, we didn't find any errors, and then it turns out that the formal model's wrong. One of the goals here is that because we think that writing an interpreter is easier, we can iterate more on checking all these different combinations. So, if something's detected, it's relatively lightweight to just mod the interpreter to do something different and see, okay, does that make it go away? I don't know if that answers the question.
Yeah, okay, thank you. So there is one question.
Thank you for the talk. This is more about example of your work, like what's the application of your work? Do you have some concurrency example for your system, or it's just for the single-threaded program?
So the question is about concurrency. That's something that we're definitely looking towards. So far, single-threaded, we were already running into some tractability problems that we'd like to iron out before we even think about doing concurrency.
Okay. So, thank you very much for the presentation. And